Hey everybody! I wanted to take a few minutes to talk about colligative properties and give you a short overview of these in order for you to either work on your homework over the weekend, because we're covering this stuff on Monday and I know you want to probably get ahead over the weekend. I also thought it might be useful to have this summary for when you go to study for the next few days. So this is Friday evening that I'm recording this, hoping it'll help you over the weekend with homework, preparing for the test next week. We'll go over this in lecture on Monday. Here's the highlights. What we're going to talk about with all those different unit concentrations that we've been using since Friday morning in class has to do with what's called colligative properties. So don't let the word colligative throw you off or confuse you. Basically, these are just properties of a species, like a molecule, that have are influenced basically by how much stuff is dissolved in them. So if we go to make a solution, then the solvent may not, for instance, boil at 100 degrees anymore. If we put solute in a water solvent, we may raise the boiling point. So I want to explain that to you briefly using these next few slides. Here is the summary of colligative properties that we're going to talk about. I mentioned boiling point on the previous slide. That list also includes freezing point and vapor pressure. So there's three equations that we're going to use a lot of math for. Here's vapor pressure. When we have a pure species, that's going to be considered our solvent. When we add something to it, the mole fraction of that solvent is going to lower. That means the pressure of the solution is going to lower. Okay, that's the first phenomenon. When we have a pure substance that we add some other things to, like a solute, the boiling point, that's the next thing we'll consider. It's going to increase. That delta, remember, means change. That means the boiling point is going to change. And it's always going to change in the same direction. It's going to get higher. The last thing is freezing point. That's where we melt too. We talk about that the same way. Freezing point is always going to lower. Now, there's some numbers in here that you're going to be given. So for instance, KB, capital K, lowercase subscript b, is going to be given for whatever solvent you're talking about. Like usual, we're going to start with our solvent as water. So we don't want to start with anything real crazy. Water is going to be our solvent. We'll consider other stuff too, but this value right here is the easiest one for us to just convey for a general case of using water. Kf is some constant associated with water, okay? Water shows up again. So what do we need to be able to calculate these units of concentration? Little m, molality, same thing here. Chi for the solvent, remember what that is? Mole fraction, okay? These are given down here. The reason I made this slide this way is so you could print it out and have it handy. Oh, so note that I have a reminder right here about chi solvent. It's always going to be less than 1, so it's part of a whole. The whole is 1. All right, so here's Raoult's law. That's the first equation. I'm going to go through these three equations in a little bit more depth and, of course, give you a full-on lecture on Monday. Raoult's law is the equation where we use the mole fraction of the solvent times the original vapor pressure of the pure solvent. This little guy, superscript O or 0, usually is some kind of starting, initial, unchanged. So if this value chi is less than 1, and whatever this number is given, then we're going to get a vapor pressure of the solution that is lower. Okay? So all of this kind of ties back to the idea of if you're able to make a solution, it's because the solute and solvent must want to hang out together and have some decent intermolecular forces, and so they're probably not going to vaporize quite as much to the same pressure. That's the idea. So the vapor pressure is going to get lower. So the math isn't too scary. Remember, we talked about in class on Friday morning that chi of the solvent, I'll go back one slide, is solvent, moles of solvent over moles of solute plus moles of solvent. So all of these slides are available in your slide packet. I'm just deleting a few that we're not going to cover in this short video. So I hope Raoult's law is looking good to you. Not too scary. Units of pressure are going to be the answer because mole fraction has no units. One way to visualize vapor pressure lowering is to think about a phase diagram. Remember, a phase diagram has pressure on the y-axis and temperature on the x-axis. We think about raising temperature to get things to change phase. You can do the same thing with changing pressure. I've compared this shape to a wishbone. That's roughly what it's going to look like for a lot of substances. It'll change depending on what the substance is. But remember, solid, liquid, and gas show up in those different regions of this wishbone puzzle. And when we look for instance, the vapor pressure lowering, when we go to visualize it, let's consider what's happening at 1 atmosphere. 1 atmosphere is atmospheric pressure. That's the pressure of the molecules that are around us right now per unit volume. If we trace from 1 atmosphere on the y-axis over to the liquid gas line, the vaporization line, and drop our line down, what does that temperature tell us? That's the boiling point, okay? Remember, the boiling point is when we've made our vapor pressure equal to the external pressure. So that's the temperature at which this guy is going to boil, okay? For water, it would be 100 degrees. What happens if I start to change the makeup of the solution? You know what it does? It changes the phase diagram, okay? It actually changes the phase diagram. So the wishbone moves, okay? So if we look at where we would trace over, I'll animate this line and you can see it pop up right at the end and hit the red line. We drop it down. Where's that intersect the temperature axis? At a higher point. So that higher point is the new boiling point. And it's the new boiling point for the solution after we've added solute to the solvent. So for you visual folks, I hope that helps you illustrate, or visualize, I should say. I hope that helps illustrate why the boiling point changes. The previous slide, before all my animation, shows you how to calculate how it changes, okay? Let me go through that for boiling point, shall we? Okay, so for boiling point, we have a different looking equation a little bit. So we have a change in boiling point, and that equals the molality. Remember, lowercase matters. It's not molarity, it's molality, because it's a lowercase m, times some constant. I've already mentioned that the constant will be given, and right now we're just considering the constant for water. So we're going to have a solvent that's water, okay? So as an example, whatever you calculate needs to get added back to the original boiling point if I ask you what the boiling point is. So if you calculate a delta TB that's 1.5 degrees, that answer is the change in boiling point. It's also in the direction of increasing the boiling point. So I have set up a mathematical statement that tells us how to calculate it, but you also should just remember whatever answer you get for the new boiling point has to be greater than the original boiling point. This is where our units matter too. Molality needs to be the unit of concentration. Here's that example KB that I mentioned. Let's visualize this too for, I believe, freezing point. That's what we'll consider next. Our freezing point is going to be illustrated on the solid liquid line. That's where we would melt if we were going from solid to liquid, freeze if we're going from liquid to solid. Trace it down to the x-axis. What does that temperature represent? The melting point or the freezing point? What happens when I change the solvent from a pure species to a solution? I actually change where that wishbone shows up on our phase diagram. There it is. Now it's in red. When I draw my line from the 1 atmosphere, drop it down to temperature, I show up at a lower temperature than before. My solution is going to melt or freeze at a lower temperature. We call this freezing point depression. Don't get depressed over it. It just means you're lowering it. Why we call it depression rather than lowering is depressing to me. Freezing point depression for non-electrolyte solutions. We'll talk Monday about what I mean by that, the non-electrolyte part. Delta TF, that's our change in freezing point. Remember, we're talking about a change from our original freezing point. Which direction is it going to go? It's going to lower. For example, if we calculate 1.2 degrees for my delta TF for water, then my new freezing point is negative 1.2 degrees. Remember, this is freezing point depression from our original freezing point. Water is 0. We're always going to get something lower than 0 for a freezing point depression for water. We're always going to get something higher than 100 for a freezing point, for a boiling point for water as well. Here's that example constant that you will probably see. Again, it's for water. Here's that same summary slide again that you have in your slide packet. Very useful summary, especially when you're working on homework. Hope this helps you get through the weekend all right. Take care.